anode and a cathode, and electricity flows between them, which is what turns on whatever it is, your phone, your computer, whatever it happens to be. And then there's a bunch of chemistry that goes on inside the battery to actually make it work. And in particular, lithium-ion batteries, without going too much into the chemistry, basically have a material on the anode side called graphite, which is kind of similar to what's in pencils. Graphite does not like to have lithium in it, but it will take it if you push it in there. So basically, they get this graphite and they push a bunch of lithium into it. The graphite's kind of unhappy, but it's okay with that. On the other side, on the cathode, they have another crystal structure, usually some cobalt dioxide that really wants lithium in it. And if you put those two next to each other with some kind of liquid that the lithium can flow through, then the lithium will really want to go from one side to the other. Problem is that in order for that to happen, this has to do with kind of complexities around the crystals, you also need electricity to flow from one side to the other. And that's basically how the battery works. So you put these two materials together, lithium really wants to go from one side to the other, but it needs electrons to go along with it. And so then you can connect this side up with a wire and allow the electrons to go through, and then you get lithium flowing one way and electrons flowing the other way, and now you have electricity out here to go do whatever magic you want to have happen. Does that make sense so far? And I can take any questions at any time. I've got kind of like follow-on things here, but that's kind of basically how a battery works. A rechargeable battery is cool because it can go both ways. So if you have just kind of a, like your Duracell or Energizer battery that's not rechargeable, then basically lithium will go one way, but you can't really make it go the other way. The chemistry is just not set up, and the crystals aren't set up to kind of push it back the other way.
So the battery is discharged and all the lithium was transferred to the other side?
That's right. Yeah, exactly. And then you can charge it by essentially pushing, you can force electrons to go the other way, which kind of forces the lithium to go in the opposite direction, right? So it's at the beginning, right, this graphite doesn't like lithium in there. You can basically push it in there, cram it in by charging the battery and by kind of pushing electrons the way that it doesn't normally want to go. And then discharge is, all the lithium going back and forth. So basically, every time you charge and discharge your phone or your laptop or any of those other kinds of batteries, lithium kind of moves from one side to the other, along with the electricity that's flowing on the outside. So that's kind of high level what that looks like. There's one piece in here which is really important called this separator. And then remember what I said before, that this kind of occurs in a liquid called an electrolyte that allows lithium to move through it, but it doesn't allow electricity to move through it. If it allowed electricity to move through it, then obviously the electricity would just kind of immediately go from one side to the other. You wouldn't be able to actually store any of your power. So what does that look like in real life? All right. So Tesla makes batteries. They look kind of like that. Which, when I arrived at Tesla, I was actually surprised to realize that their giant car battery is made out of thousands of those, which aren't that much bigger than like a AA battery. So they basically just string together thousands of them to make one giant battery. We'll get to that in a second. But inside this battery is this. So, a little bit maybe. Cool. So basically, so what's happening here? So basically they just took those two sheets in the previous picture, they make one really, really long version of it, and then they just wind it up into a roll and cram it into this battery. And so what each of these lines here are actually either the anode, which they make out of copper, or the cathode, which they make out of aluminum. The kind of dotted gray stuff on either side are those crystals, the graphite or that carbon dioxide. And you can see they're super close to each other, right? So lithium goes from like this little piece here out to this little piece there when you discharge. And then that separator, which is that important part, is basically a thin sheet of plastic that just separates them and prevents this copper anode from touching the aluminum cathode. And who wants to guess what happens if they actually touch by accident? Yeah.
There's a short?
Yeah, there's a short, and then the battery will explode. So that's what's tough about these batteries. The reason they're constructed this way is because they want to cram as much in there so that your phone doesn't die in 2 hours, even though sometimes mine does. Your laptops last long, and cars can go a long distance and everything. So there's kind of this fight between cramming as much chemistry as you can in there, but leaving these things super close together and vulnerable to breaking and then blowing up. And so that's kind of the big battle in battery making. And that's a lot of what we did, worked on at Tesla. So real quick, before we get into kind of what can go wrong, this is what a Tesla battery looks like if you open it up. And these are all pictures on the internet, so technically no one's supposed to see them, but they're everywhere. It used to be secret. But this is basically what is at the bottom of a Model S or the Model 3 or any of the Tesla cars. And what we're looking at here, so this is basically the size of a whole car. This is kind of like the floor of the whole car, and the wheels are kind of here, and over there. And then each one of these little dots is a battery. And so this has thousands and thousands of these batteries. I think the Model S has maybe 8,000 of them, kind of all strung together to make this one mega battery. And there are a couple of safety issues that we really wanted to pay attention to here. And the issues were two. One was we wanted to make sure that if anything happened to one of these batteries, that if one of these batteries explodes, maybe I'll ask that. If one of these batteries explodes, kind of what's the issue that someone can foresee?
It will affect other batteries around it.
Exactly, right? So if one goes off or a few go off, it can start a chain reaction that will eventually just kind of cause all of them to go off, right? And so that's what's called a thermal event or thermal propagation. And maybe kind of skipping ahead for a second. This also is on YouTube, right? You may have seen some of these videos, which look like this, right? Which is kind of not so good, right? That battery pack is now on fire and basically kind of having a reaction that's spreading through the whole thing. So that's scary. Now, before we kind of get into like electric cars and everything else, they are actually much, much safer than gas cars. Just think about it. You have a tank of gasoline can easily explode. So there's a lot of kind of articles about, are electric cars safe and all this other kind of stuff. And if you look at the statistics, they actually are a lot safer. But they will fail in certain ways, the same way that normal cars will get into accidents and light on fire also. And so that's what that can look like. And so if we come back here, our job at Tesla was to make sure that actually looks kind of like it did. That you have a bunch of fire that's kind of going out the sides of the car and not into the passenger compartment where people can be. So that if you get into an accident and something goes wrong, people can get out of the car safely, and then firefighters can come and put the fire out. And in much the same way, gas cars are designed the same way. The gasoline tank is kind of in a particular location and protected so that if it does light on fire, people have as long as they can to escape from the vehicle before getting hurt. So that was one thing we focused on at Tesla. The other thing we focused on was we wanted to make sure that if one of these things went off, if only one went off, that it didn't actually propagate and it didn't actually set off this chain reaction. And the reason for that was, you can imagine, if you think about the numbers, there are about 10,000 here in this battery pack, and they're selling like 100,000 cars a year, which actually isn't that much. They eventually want to sell 1 million. Right? You have billions of these batteries kind of running around all over the place. And making billions of something have zero defects and no kind of issues that randomly make is really, really, really hard. And so the battery companies like Panasonic are pretty good at that. And we also wanted to make sure that even if they made a mistake and one went off randomly, it wouldn't set off the rest of the car. So those were two things that were really tough. And we did a whole bunch of experiments out of Tesla, which were pretty awesome experiments that allowed us to kind of design that. One thing that I think I did want to show is, this again is something you definitely shouldn't try at home. I tried to find like a version of what we would actually do at Tesla, but this is just some homemade YouTube video. But anyway, the batteries are quite violent. So again, there's that kind of play between packing as much energy into these things as you can versus the safety aspect. But I think as one of you pointed out, right, if they heat up, they explode, and then they can easily heat up their neighbors. So this is kind of what that can look like. This is just a battery on the stove, which obviously you wouldn't ever normally do, but they go pretty hard. So this is why people are super careful about it. So if you get the the announcements on you hear the announcements on the plane, like don't put your lithium-ion batteries in your luggage and all this kind of stuff. People are kind of scared of essentially that happening on these planes. This was also why I don't know if you guys remember, like the Galaxy 8 phone that was recalled a few years ago from Samsung. Right, they had problems with their batteries. This was this kind of, they're going to put hundreds of millions of these phones out there. They got to make sure there are no defects. The reason they recalled that phone is because they just didn't know why it is that those batteries were kind of exploding spontaneously, and they had to get them off. That unfortunately was a $10 billion mistake for Samsung. So that's why we pay a lot of attention to it. Cool. So I think that's kind of most of what I wanted to say. A lot of the experiments that we did at Tesla involved kind of simulating, this was the kind of cool part of the job, involved simulating essentially what a car might encounter if it's just driving around on the street, right? So we did all kinds of stuff like puncturing these battery packs as if a car like ran over some sharp object and then kind of hit it from underneath. There were some pretty crazy tests that NHTSA, which is the kind of government agency that runs battery safety, required Tesla to do, and requires all kind of EV manufacturers to do. One of them was, they get very creative, there are all kinds, but one of them that I thought was most interesting was if an electric car gets into an accident with a gasoline car and gasoline flows under the electric car and then lights on fire, basically under the car, then does the battery take long enough before it then lights on fire? And so for a lot of those kinds of tests, we would drag a battery pack out to the Nevada desert and put some gasoline under it, light it on fire, and see what happened. So you can imagine that those got pretty exciting pretty fast. And we would do tests kind of at all the different levels. So we would test like entire battery packs like this. We would test these kind of chunks called modules, where the cells are really, really close together, and we would test kind of individual cells in, much more professional kind of versions of what we saw there. These kind of little chambers that we would use to either heat them up or poke the batteries or do all kinds of stuff and figure out ways of reducing the chances of that kind of failure happening. Maybe the last thing I'll say about how we designed these packs, or kind of what were the ways that we could mitigate it. One of the things that we tried to do was, inevitably if someone got into an accident, enough of these things would go off that would cause the rest to go off, and there's really no stopping that. Like we knew that we'd never be able to prevent that entirely. So as I mentioned before, we tried to make sure that we kind of propagate as slowly as we could. One of the ways that we tried to do that was create these modules, which are kind of subsets of cells, and then wall them off from each other. So you'll see that all of these modules are kind of themselves in like a big metal casing. And we would do all kinds of fancy engineering to make sure that as this thing kind of went off and as the cells, would kind of propagate through, that all the hot gas and everything that would come off of it would go out the side of the car instead of out, through these packs and then kind of light off other cells more quickly. So there's a lot of kind of complex but pretty neat engineering that we could do and experimentation that would follow. And I think that's what I got on batteries. But happy to take any questions on how batteries work, battery safety in general, any of that kind of stuff.
Oh, so you said that big battery is made of like tiny little batteries?
Yeah.
So when you recharge like your Tesla, so how does that work? Do you like hold them?
Yeah.
Just charge it?
That's a great question. So that is a pretty complicated problem that is solved through a lot of kind of computers and chips that monitor and make sure that all of them get charged in the same way. So basically the way these batteries are linked up, so there are many of them that are linked up in parallel, which allows for kind of more current for the same voltage. So they usually have maybe like several dozen, 70, 80, something like that in parallel. And then they'd have a bunch in series, which would increase the voltage. So they'd end up with a pack like this that would actually have a voltage of, say, like 400 volts instead of like the usual 4 volts for a battery. And then a bunch in series so that it can make a ton of current and have enough power to run a car. And one of the problems that can come up with that is when you charge it, you have to make sure that all of those batteries are charged the same way and that you don't end up with one battery that gets charged too much or too little, because that can also damage all the battery components and then cause exactly one of these problems. And so the way that they would solve that is they had little chips attached to each of these modules that would actually measure exactly what the charge was for each of the individual battery components in the bigger kind of stack. And if any of them got imbalanced, then they would kind of direct current one way or the other to make sure that they all stayed at exactly the same charge as you went through kind of all these charge and discharge cycles. So through that kind of complex engineering, they ended up with basically all the cells would all discharge or charge kind of at exactly the same rate. Yeah.
Like, what makes a battery explode? Like, you said when the two sides touch, right? But
Yeah.
when you make it, like, how do you, like, if it's a defect, doesn't it already touch? So why doesn't it explode when it's made, and then why does it like explode when
Yeah.
you actually use it?
That's a great question too. So it can, if the defect is big enough, then yeah, it won't even leave the factory, right? And you won't even really be able to charge it. And so they'll have some kind of, like in the Panasonic factories, they'll have some failure rate because there was some connection in there that just prevents you from even charging it. So that's fine. The defects that are kind of more, a bigger problem are the ones where it's small enough that the battery will work kind of a bunch of times, but eventually the defect causes the battery to fail maybe after you've charged it, 100 times or 150 times or something like that. And part of the issues that you can run into, if we go back to this, if we go back here, is these crystals are normally supposed to behave where they just kind of lithium goes out or in, and the crystal itself kind of stays the same. The problem is that if you do overcharge it a little bit or discharge it a little bit, or even kind of during normal charging, those crystals kind of grow and flex and do all kinds of stuff at this micro level. If there are defects in the crystal, then the crystals can actually kind of pile on top of each other, and you get these little like fingers that can weave their way kind of over to the other side. Defects like, if this metal piece here is thinner in one section than it is in another section, that little section may get slightly hotter every time you charge, or may get actually have a slightly higher voltage because of kind of resistances every time you charge, or things like that that can actually cause this kind of growth that can lead to damage maybe 100 or 200 or 300 cycles down the road. So they have to be very, very precise about kind of how all that is put together. Yeah, that's a great question.
Why does a rechargeable battery lose capacity over time, or best practices in terms of like charging it to maintain capacity?
Yeah, so it loses capacity over time for kind of the same reason that these defects can grow, right? So these crystals kind of grow and shrink, and there are all kinds of dynamics that happen to these crystals every time you charge it. So even though they're built to release the lithium and kind of suck them back in, they don't completely like that. So every time you charge it, there can be like additional defects that happen in these crystal structures that prevent lithium ions from kind of going and lodging in the same way that they used to, and then those defects will kind of grow as the cell kind of becomes older. So one of the issues there is it's a compounding effect, right? Where if you're charging and discharging your battery at a normal rate, and then all of a sudden, the crystal itself is kind of starting to lose capacity. If it loses 10% capacity, that other 90% now has to work as hard as the original 100% was working. And so it's overworking, which causes it to kind of degrade faster, right? And so then you'll get this kind of, batteries that'll last a while, and then all of a sudden it'll just kind of tank. Best practices, it depends on the type of battery, but the best things that you can do are kind of, the ideal case would be anytime you're not using your phone or your computer, you leave it at like maybe 80% of the charge. Or maybe 90%, something like that. Like a little bit below 100, just because, again, commercially battery makers want to kind of cram as much energy as they can, so 100 really kind of pushes the limit, like how much you can get in there. So if you were to charge it to 90 and then leave it at 90 basically its whole life, you'd probably get more life out of the battery. Leaving it at a super low state of charge can damage it more. And so if you have a choice between like keeping your computer plugged in all day or letting it drain and then come back and then drain and then come back, you should probably keep it plugged in, just because those cycles again kind of exercise the battery itself and will cause that to reduce. And then one of the worst things you can do is just leave it unplugged forever and then let it kind of discharge all the way. Most battery systems will have one of these little chips that kind of recognize what the voltage is. If the voltage gets too low because you haven't charged it for too long, oftentimes that chip will essentially say, this battery's dead. Don't charge it again because it actually might have grown like a bigger defect because you really went too low, and it's not safe anymore. And so sometimes if you leave, if you get a very, very old phone that, you upgraded your phone, you had some phone that's just left in the closet for 2 years, you go and try and plug it back in, it just won't even turn on. And usually it's because of that battery is now registered itself as like over discharged and no longer.
How are we planning on like disposing of or recycling these batteries as they age?
Yeah, that's a great question also. So there are more and more facilities that are being built in order to tackle exactly that, the more and more electric vehicles that come out. The ways they do it are pretty interesting and kind of complicated. I'm sure this has evolved. So the ways they did it 7 years ago when I was at Tesla was oftentimes they would get one of these old batteries, go to some plant. They would actually just dunk the entire battery into liquid nitrogen and freeze it because there's all this kind of complicated chemistry in there, and then basically just kind of, in a way, kind of blend the whole thing and then separate out all the metals and then go and recycle them. And so then they can recover like the copper, the aluminum, all the graphite and materials and everything else. There's definitely some component there that is, there are certain components that are easier to recover, like the metals, and then there are certain components that are a lot harder to recover, like all of the lithium crystals and everything else. But I think that's something that people are working on and they know is a big issue.
How does a battery maintain a specific voltage? And also, as far as I know, when it loses charge or if there's too much current draw, the voltage drops, so it's down there.
Yeah, totally. So those are all good questions too. We don't have control on it. Do you have a marker? Sweet. So they try to maintain a specific voltage, but they actually don't really. So usually the way a battery, like a discharge curve will look, is oftentimes lithium ion is like 4.2 volts, although that can change depending on the exact chemistry. But it'll usually look kind of like this, and then it'll steadily drop up until a certain point, and then it'll go down really, really fast. And usually this is considered like fully discharged. And then down here is like this is too low and heavily damaging the pack. And then up here, if you were to kind of keep charging it, it would kind of go like this, and then eventually it would break, where you could now charge it as much as you want, except it's not really charging anymore. So this kind of, I don't know, goes wonky over there. And oftentimes here, this is like maybe 3.5 volts or something like that. So most electronics will be basically built to work anywhere between these two voltages. And that's essentially on the kind of electronic side to be able to withstand either of those, depending on what the state of charge is. But this is why, for example, like a Tesla car will be get its best acceleration when it's fully charged, and then it'll get a lot less acceleration when it's almost empty. And that's just because the voltages are all lower, and so you can just pull out less current. And then what was your second question?
I guess, like, why does the voltage drop when you draw so much current?
Oh yeah, so batteries have resistance in them. So if you remember the picture with all those thin pieces of metal, that metal is super thin. It's like foil, except like thin foil. And so when you pull a lot of current through there, that current has to go through these very thin sheets of metal and this big, big coil and all kinds of other pieces in the battery to get out. And so the battery itself has internal resistance there. And so when you draw a big current, then that resistance comes into play, and you end up kind of burning up energy on the way out of the battery, which is also why if you draw a big current, batteries will get really hot, right? So if you're, I don't know, FaceTiming, on your phone or something, you'll notice that it heats up. Most of that is the battery that is heating up because you're just drawing so much current there. Same thing for your computer. So that causes that voltage drop. And that voltage drop can be pretty big. And that can be another source of these kinds of defects and things is, if you really want a lot of current here, right, you can be at 4.2 volts. But then if you really want to pull a bunch of current, you may kind of connect up the ends such that this 4.2 volts just kind of plummets, and then it hangs out here, produces a ton of current, and then comes right back up. And then, now it's here. So you've actually used like this much energy in the battery, but in order to pull it out really, really fast, you kind of hooked up some electronics with a very low resistance on the outside and just kind of sucked, electricity out of it really, really quickly. So that can be another way the batteries can get damaged, particularly if this voltage is kind of lower than like the lowest voltage that it likes to hang out.
Are there any particular reasons when the battery state gets a cylindrical shape?
That's mostly just, so there are two main shapes that they take. So oftentimes they're cylinder, and then the other shape is flat, or prismatic is what it's called, right? So like in a Mac computer or your phone, those are all prismatic batteries. And so they just have multiple layers of the sheets that are all kind of stacked together flat. The cylindrical ones you can pack much closer together. And they are, in some ways they're safer in the sense that you can kind of contain the battery itself into this smaller cylinder and prevent one piece of it from touching another piece. These big prismatics are actually themselves contain a lot more energy than one of those individual cells. And so if something goes wrong, there are fewer batteries for there to be something that goes wrong with it, but if it does, then there's definitely no stopping it from just kind of consuming the entire battery. So those are kind of the trade-offs there.
For a rechargeable battery, I'm guessing the reason they have specific chargers has to do with that curve. Start following it. If say I had a completely depleted like 4.2 volt battery, I was like, let's just plug it into DC power supply 4.2 volts.
Yeah.
In a pinch, would that work? I want to do it, but in a pinch, would that work?
Yeah. So it depends on how much current that 4.2 volt power supply would push. So there are two things that happen when you charge a battery. Let's see if I can remember these things. So what you want to do when you're charging a battery is kind of hold a, let's say this is current with time, and you're charging. You want to start out by holding a constant current that is a safe current to charge at. This current will require that the battery itself actually not be charged at 4.2 volts, but charged at kind of a slowly rising voltage that's enough above 3.5 that you get this kind of fixed current. And so oftentimes what you'll end up with is a current curve that looks like kind of fixed current here, and then it'll hit 4.2 volts. And then once it hits 4.2 volts, you hold it now at 4.2 volts, and then let the current kind of drop to 0. And then you call it charged. The reason you want to do that is because too much current can damage the battery and too much voltage can damage the battery. And so you want to just kind of max out the current until you max out the voltage, and then you hold the voltage and the current will drop. You could always charge it at a higher current, right? This curve is kind of a theoretical curve that goes, something like this. So if you wanted to charge it super fast, you could just put a ton of current in there, and it'll charge really, really quickly, but it'll probably get damaged pretty quickly also. It'll also get really hot because, again, that internal resistance, a lot of this current ends up getting burned up in that internal resistance, which can be dangerous because if the battery gets too hot, you can melt that plastic separator and then the battery can explode. So those are kind of the complexities there.
So then, those new sort of wall adapters, like fast charge for browsers, is that causing more damage to your phone battery then by using that versus regular one?
It is definitely going to be harder on the battery to do fast charge than not. So if you don't have to fast charge, then you probably shouldn't, which is also why, I don't know if you guys follow the Tesla fast chargers and all this kind of stuff, right? The reason they don't put those in cities and the reason they encourage people to use them only on long trips is because they don't want people to just go to a fast charger like they do to a gas station in the middle of the city. They want them to charge them more slowly at home. If people went and fast charged them every day, then they would end up, the car battery itself would end up kind of dying very quickly. So you definitely pay for fast charging. And on the flip side, there are all kinds of stuff that you can do to the battery chemistry to make it kind of easier to fast charge, which is what a lot of people are working But that's fundamentally why it's really hard to develop a battery that charges super quickly, right? So they have these, the latest, warranties and stuff like that. But they would warranty the battery for some certain number of miles and some number of years. And so they basically knew that, assuming people drove it like normal, then it would last this long, and then they would give you a new battery. But yeah, eventually, if your car gets old enough and it's out of warranty and everything else, then you'll need to get a new one. But I think they're targeting having that kind of be the same as like the engine on your car, right? At some point, if you have your car for 200,000 miles, then the engine may need to replace the engine or change the transmission or any of that kind of stuff. The batteries, they want to build the battery well enough that it becomes another component like that.
So the batteries for the Tesla cars, is that specific to Tesla, or do like other electric cars use like similar design?
Yeah. Tesla, I don't know now anymore, but definitely back then, and I think still for the most part now, Tesla uses a particular chemistry. So the one, they use those cylindrical cells, which certainly 5 years ago, most of the other EV manufacturers were using these prismatic cells. They also use a particular chemistry, which allows for cramming ever more power into that cell. So the reason Tesla cars can go so far is because they kind of took a chemistry that they could cram more energy into, which is more volatile and is definitely harder to deal with, and then they put a ton of engineering into making the battery safe anyway. So that was the hard part. Most of the other facilities, or most of the other manufacturers, decided to go with a different chemistry that was safer, that would kind of explode less violently and all this kind of stuff, but it could store less energy. And so that was definitely a gamble on Tesla's part that I think they worked, and they, all humility aside, hired, I think, an awesome team to make sure that we could really make the battery safe, even though they actually had all this energy and all this capacity in there. So they're definitely kind of out there in terms of using the most advanced chemistries and then putting the most advanced engineering into creating this safe environment anyway.
With those smaller individual cells, can you detect failure in specific one? And if you do, how easy is it to replace a specific?
Yeah, for the car?
Yeah.
In the car, not really. You can definitely detect failure unless a battery. So part of the hard part is that all these batteries, like I said, there are maybe 70, 80 of them in parallel. So even if one is kind of in trouble, it's hard to pick it out because it's got 79 around it that are working just fine. So it has to really be in trouble in order to kind of identify that. There are things that they can do to kind of see that and then adapt to that, or alert the driver, or alert Tesla and things like that. But for the most part, they're relying on the manufacturers, which is mostly Panasonic, and now Tesla's making their own, to build them well enough that's basically never an issue, or the chances of that are very, very small. If they do detect a problem, and this is why all these kind of over-the-air software updates that Tesla sends out for safety and all kinds of stuff work. They have all kinds of components in there that they can use to divert power and electricity in various ways to make sure that the batteries themselves kind of stay safe. And they can upgrade their algorithms, they can upgrade their detection and all this kind of stuff to try and pick out issues as they see more and more issues that can possibly go on.
Well, if there are no more questions, thank you so much for coming in today.
Totally.
I really appreciate it.